have started recording. We had a lot of problems with starting this lecture, so sadly it will be only available in recording for external participants. We will try to solve it next time. So my talk will be today in two, I expected three parts, but since our technical problems, probably only two, we will have time only for two. First of all, the description, the very short description about the Troitsk mass experiment in search for neutrino mass. As always, please don't hesitate to ask, at least people that are here, please don't hesitate to ask questions. And this talk was done in Quartz conference in 2018, just before the pandemics. And I will try to skip details and keep on the important parts. The experiment, here you see the picture about motivation, about dark energy, dark matter, so you probably know we have some kind of problem in physics that most of the matter in the universe and most of the something that keeps the universe together is not seen. It's dark, meaning it's not radiate light. But and actually, when people first began to think about it, they said, okay, there are neutrinos, there are particles that do not interact with anything, and maybe it's a mass of neutrino. And one of the key things that first Troitsk mass experiment showed that no, you can't explain the dark matter by the mass of neutrino. Mass of neutrino is too small to explain the dark matter. And now we are working on the sterile neutrino problem, and it is possible that a heavy sterile neutrino could explain this. So what I want to talk about, I used to use this presentation for, is to explain how the experiment worked. Here you have a more or less modern photo of the setup, and here the large part is the spectrometer, and here in the here is a liquid nitrogen tank and the detector, and back there we have a okay, probably I just forgot to share screen and nobody told me about it. Yeah, it's a little bit strange. I hope that now there are no problems. Yeah, you see. Okay, now you see the picture and it's fine. Okay, let's move forward. The basic idea that you have a bit beta spectrum and beta decay, and there is a well-known formula for the shape of the spectrum. It's a Fermi spectrum. If you know physics, it's okay. After the third year, you probably know about it. If you are not in physics, it's not quite simple to get the theory. I mean, but it's a standard thing right now. It was developed at the beginning of the 20th century by Fermi. But what is important for us is the shape here. Let's move forward. And here we have this setup. And we have a spectrometer, the detector, the tritium source, and some kind of pumping system, which takes the problem is we are working with the tritium. Tritium is, of course, radioactive. But the problem is that it's a beta decay, and of course we want to avoid just tossing radioactive gas in the air. But the problem with tritium is that tritium is an isotope of hydrogen, and so when you breathe in the tritium, it replaces the hydrogen in your body, and it's very bad for yourself after all. So if you want to work with the tritium, we need to use this gas here, pump it here, and then pump it out. Because if any gas comes here to the spectrometer, we will see completely a wrong picture. And the energy of the beta decay is so small, it's like 18 kiloelectron volts, that any foil, any window here will distort the results. So it's in fact, this pumping system is a wonder of engineering art, and until recently it was unrivaled in the world. What is important for us is that electron born here then transported, and it can interact with the different atoms inside the tritium source, and then it's via magnetic field it's transported to the spectrometer. And in the spectrometer we have a combined electric and magnetic field, and we have you can see the plots of magnetic field. So it's like this magnetic reflection points. I mean, if you do not know what it is, just read about magnetic reflection. And we'll have an electric field lines. So the electrons are decelerated to the center of the spectrometer, so-called central or analyzing plane, and then accelerated back. What is important is that if you apply the retarding potential like close to the energy of the electron, then electrons with the energy larger than this potential will come to the detector and will be registered, and electrons with a smaller energy will be reflected back. It allows us to measure the spectrum with the precision of several electron volts, which is like almost 1,000 times better than the best detector you have now. Right now you can have detectors with like 300 electron volt precision. So, but still, if you are going to the precision of several electron volts, it's 100 times better than you can get with the simple detector. And important thing, of course, that you get the integral spectrum. You're shifting this potential by steps, and if you have retarding potential like 17 kiloelectron volts and 17.5 kiloelectron volts, you will have all the electrons with the energy higher than 17.5 kiloelectron volts, and you're just scanning the whole energy region with this retarding potential. The spectrometer itself is a rather complicated structure because we need it to be a perfect cosmic vacuum. The vacuum is about 10 to the minus 9 millibar, and tritium purity is even several orders of magnitude better. But it also have to have magnetic shielding, magnetic compensation coils, bakeout strips, etc., but we will not discuss it today. Yeah, what happened? Okay. Here's a history. It's a very old experiment. In fact, it was started the same year I was born, so we are the same age. And here is the spectrum, the part I wanted to focus on today, and this is why I took this presentation. As you can see, the actual spectrum, calculated spectrum of the electrons is rather complicated. You see here the basic beta spectrum, the one I've showed you before. Then you'll have a transmission function. It has several parts. Mostly it's a loss of energy inside the tritium source. So you see when those electrons inside the tritium source hit other molecules, they lose energy, and this distorts our result. It's very important. We need to account for those losses statistically, of course. And then they have a spectrometer resolution, and I think I'll have a picture later showing its shape. There are different corrections to the shape as well. Basically, it's just a step. It's an integrating spectrometer, but there are different corrections to this as well. And we need to compute double convolution to get the proper result. And on this picture, you see that it's not a double but triple convolution because in order to get the tritium spectrum itself, you need to also sum up all so-called final states of the tritium molecule. When it decays, it could have different residual energy with a different probability. And we have then triple convolution which raises a problem of performance, actually. Because if you need to get one integral, like 100 points, is okay. If a double integral, it's 10,000 points, maybe it's okay. And if it's a triple integral, you have 1,000,000 points, and it takes a lot of time to compute. Here we have a sterile neutrino addition to the spectrum. It's not that important right now. And we have a loss shape function, which also would be computed. The probabilities themselves need to be computed. The probability of scattering, where x is an effective source thickness, and also those loss functions, loss probabilities, energy loss probabilities should be taken into account as well. I'm not sure I have a slide for the loss function, but we'll see. The resolution function looks like this, so it's more or less a step function. Of course, it's not a step because it has a finite size and some specific peculiarities on the size of this step. It's not important if you are talking about the scale of 10 electron volts, but if you are trying to measure the neutrino mass, which is of the order of 1 electron volt or even much smaller, then it's important that you take all those things into account. Okay, I do not have a loss functions here, but loss functions are taken from the experiment, and there is some additional mathematics to compute subsequent loss functions for single scattering, double scattering, etc. Those systematics effect like wrapping, I think I will skip it. Well, this one is important because it's one of the primary effects that should be taken into account. As I said earlier, we use a spectrometer, so the detector is working in the so-called Geiger mode. So it's just counting particles because we get spectrum from the shift of the retarding potential, not from the detector. But the detector itself, it's a silicon lithium detector, also has some kind of resolution, and it's important because it allows us to clean up the spectrum, to clean up all parasitic events and to understand better what are we measuring. For example, you can see on this picture there are two problems actually. This problem, here we have a spectrum of electrons coming to detector at a fixed retarding potential, and the different lines correspond to different retarding potential. And you obviously see the lower the retarding potential, the more particles you get. It's obvious. But this thing is a pileup, meaning that the two particles coming more or less at the same time, they will produce a single blip in the detector with a higher amplitude. Since we are, it's very important for us to get very precise measurement of the count rate. Those effects should be taken into account. One of the articles I gave you in the list, our students, is about detecting those time irregularities. Another much more important problem is this cutoff threshold. You see, this one is not, it's a physical, it's not our physics, it's a physics of the detector. If the energy of a particle is less than the detection threshold, it's not detected. It means that here we have a spectrum. I won't talk right now about why the spectrum has this shape, and that's a very interesting question actually. But what is important is that we cut its tail. So if we just, I'm not sure we can use, no, I have a highlighter, I have a pen here. So if you will just continue this line here, you will see that there is some amount of events here which are not counted if you cut at this threshold. It is important, and this part is rather significant. It's like several persons. Several persons, it's not a large sum when it comes from your paycheck, but for somebody it's large enough, okay. But if you're measuring quantities of with a precision like 10 to the minus fourth, it's quite important. It's much larger than the effect itself. So, for example, it is important to see what is here, to extrapolate this curve. Okay, and we are skipping quickly the results and perspectives. There are some results published in these articles about, this is not about the light neutrino mass. The final article about the light neutrino mass was published in 2011, and at this moment it was the best limit in the world, and it was like this until the last year when the country finally gets the better result. This plot is about sterile neutrinos with their different masses, and we have different contributions of systematical errors. And as I said, it's published, but the result is still not quite interesting because the interest from a cosmological point of view, the interesting thing starts with a 10 to the minus 5, and you see that it's so far from this right now. You see those exclusion plots. It's showing a sterile neutrino. It's for old experiment. I mean, when we're measuring light masses, and this is a more or less current situation with the current setup. It's 2 years ago, but the progress since then was not so great. Okay, Tristan, we're skipping Tristan detector, and you can see here on this plot, you can see two different detectors with a different quality. It's an all silicon detector, and this is the Tristan detector, which much more advanced technology. Okay, those people here, it's people from France, and you can see myself in both photographs. And it's the old Russian team here. This one is not interesting, but this one is my slide, since it's a bridge to the next part of my talk. And I will be discussing how the analysis of this physics is made, because the analysis is a really complicated thing in this case. Right now you can ask your questions if you want. For the first part, do you have any question for the first part? No, no questions. Okay, maybe I'm talking too fast. I hope that you will understand what I'm saying. If you do not understand, okay, yeah, okay. it's a valid concern, but there are plots and articles. They have, of course, they have titles. Okay, we are moving to the second part, and it's actually a software part, or data analysis design part. I hope you are seeing the picture. Please confirm. Okay. So in order to do this data analysis, I'm starting at somewhere like 2013. I started developing a framework, a data processing framework, because analysis is really complicated. You saw that even computing the spectrum takes a lot of finesse. It requires some numeric things. It requires understanding the physics, and the analysis even more complicated. So in order to do that, I've designed this framework. Right now, the old version is available on GitHub, but it won't be developed anymore. And the new version of this framework we are using for our, at least some parts of it, we are using for our Plotly kit, VisionForge, libraries, etc. But not the part I'm going to talk about today. Okay, you see again Troitsk mass here. and some rant about software, about scientific software, rules specifically. And now we are going to the core of the problem. Let's see. Our basic scenario of using the software to analyze something looks like this. We have a user, we have an algorithm, and this algorithm produces result. This is how you typically work when you're working, for example, with a Jupyter notebook. You just create this script and it loads some data and produces a result. That's okay if the analysis procedure is a simple one. Now we have external data. We need to load it. Okay. Now user needs to interact with external data. Sometimes user even tries to change the external data, which is not very good, but still there is interaction here. For example, you see that some kind of problem, you need to try to remove problematic points from your data or filter it somehow. For example, you want to pass filtered data sets to the algorithm. Then you have intermediate steps, which could take a lot of time, and you have intermediate data, which could be large. For example, initial data for the analysis of Troitsk mass right now is several terabytes of data. Then the user tries to interact with intermediate data because he tries to debug, he sees some kind of problem, and he tries, for example, to change data produced after some step. It's very terrible. It's a terrible practice, but people do that. You can't avoid it. If you see some problem, it is usually much easier to change some kind of data in the middle of the analysis than to do the new analysis. And logs, of course. If you're doing something time-consuming and complicated, you need logs as well. And user sees logs and he tries to adjust the algorithm and the data and the intermediate data according to logs. And of course, the user sees the result and he says, okay, I don't like this result. I will change the algorithm to make a better result. In the end, it's okay if you have a very simple data and very simple and transparent analysis algorithm. But what if you have like hundreds of data sets? If you have a tens of analysis step here, it all becomes a mess. Actually, I see this problem and people agree about this problem on each and every serious data analysis task working in the physics. So you need some way to automate all this. Okay. Now, let us state some rules for the good data analysis. The data is immutable. It's very important because when you start messing with the data, the results are unpredictable, especially if you work in the notebook environment and changing something could affect, and you can even, for example, you can miss hitting some cell and the results are completely unpredictable. In the data forge, but you need to provide some way to explain how the data should be analyzed. Otherwise, you will keep changing the script each time by hand. So we need some kind of metadata. And this metadata could be user provided, or in most cases, it comes from the experiment itself. So it explains what this data means. Yeah, that's written here. And we usually want to somehow interface different layers of metadata. The similar thing is now used to configure software like VS Code or JIT or Gradle or whatever. You have different files in different parts of your system, and you want to hierarchically request properties from your working directory, then from your system, then from your global configuration, etc. The important statement in the data post is that we need this analysis to be as declarative as we can. So we are keeping all this data and the metadata. Now, how do we merge the metadata? Consider we have different layers with different properties, and what we do is actually just layer one on top of the other. So this one will be replaced, but this one will be new, and we'll have some kind of this picture. And it works exactly the same, for example, in plotting. You can override metadata from, and in Vision Watch, of course. You can override, for example, color of the whole set of geometry primitives by placing them on the top layer. Okay, so the idea I put initially in the data forge, those almost years ago, was like this: if you have a classic analysis, everything is in the script. So user takes the data, takes the metadata, and creates a script which processes the data. The idea of the metadata processor is that you have a combined format, which like a container, both for data and for metadata, and then you create a processor which modifies the analysis process depending on the metadata you encounter. So it's kind of a declarative programming. Nowadays, it's a very widespread, but like 10 years ago, or 8 years ago, it was a novel idea. It's a similar, yes, but in the Scilern and all other machine learning frameworks, you still do not take into account the metadata. You work only with the data, but the script itself, I mean the transformation you do on your data blocks, is written by the user. Here, the idea is that the algorithm, I mean the processing pipeline, is adjusted automatically depending on the metadata. I will show you later. Okay. The second thing that was used in Dataforge nowadays, again, it's not a new idea right now, but at that time, almost 10 years ago, it was very new. Even now, I see that it could be in some areas it's very interesting. And the idea is that if you see like CERN rules, you will see that everything depends on the global variables. And global variables, probably know that global variables are bad because you will never scale your system with global variables. If one part of the system makes change to the global variable and the second part of the system requests this global variable, you will have a problem, concurrent access, and etc. And you can do a good parallel computing here. So in all modern recommendations, you will see that you should not ever use global state or mutable global state in any case, and the global state itself should be avoided as well. But not, in any case, you should not use global mutable state. But we need some kind of state. We need some context to run our computations. For example, in the previous lectures by Roland, you saw that you, for example, need to know what engine is used to make your those tensor transformations. What number of cores do you use? Where to take data, etc., etc. Where to put logs? You need a context. In modern software engineering, this is all usually solved by so-called dependency injection framework. You can Google it up. It's also called the inversion of control principle. Let it be your homework. Google up the inversion of control dependency injection. But in DataForge, I used the idea I took actually from Android development. The idea is that when you have some kind of process, you have an immutable context for this process. And this context could be inherited. And its context stores some something like system environment. It's similar to the Unix environments. When you create a new environment, it inherits the properties from the parent environment. But what is important is immutable. And in case of DataForge, it also works like a dependency injection. It allows you to resolve so-called plugins. I mean, some pieces of code which could be used for your analysis, like plotting libraries, mathematical libraries, parallel executing tools, etc., etc. And it works very well. And you see the plugins here. So we can attach a plugin to a context without changing the parent context. In the old DataForge, it was actually a mutable thing. Context was immutable, and you had to configure it first, attach all the plugins, and then to start working. Even in this case, it was better because it did not change the parent context. But right now, in the modern DataForge version, context loads all plugins on its creation. So it's fully immutable. The data flow model is also a thing all modern data analysts are more or less familiar with. It's a basic MapReduce pipelines, but again, like 8 years ago, it was a new thing. And here you see more or less a regular pipeline you have in your, for example, TensorFlow or whatever, but with addition of metadata. Let's see. First, we start some kind of action, and it takes in metadata and configures this action and produces a result. And then we need to remember that each piece of we have several pieces of data here, and each piece of data has its own metadata. So, for example, you can see two files, measurement files, data files from the neutrino experiment. And at one of them, there were one set of parameters, and another has different set of parameters. If you do it the DataForge way, then you create one algorithm which adjusts itself based on the metadata. You do not create two different scripts for different files. It allows you, by the way, to do automatically parallelize such work, because if you do not any any user input on how to process those files, and it all is inferred automatically, then you can do it in parallel, also automatically, or even distributed system, because as you see, there is no user input here. And this is so-called push pipeline, where you push the data here and each action processes it. And there are similar things in Python ecosystem. But let's see much more advanced pull system. Let's assume that you have several terabytes of data, but you do not want the several terabytes of data. You want to process only part of this data. And even the workflow could be more complicated. Some tasks you want to work are working with the already provided results. So we want not a pipeline, but something closer to push system. Push system. make a build system. For example, Gradle or GNU-Make. If you listen to the lecture by Andrei Sheglov last week, you heard about the Make, about how task works. We want exactly the same. We want those tasks to be computed lazily, only on demand, and we do not want to recompute tasks which for which results are already processed. It's a complicated thing because, as we remember, the tasks have parameters, configuration. So you need in order to cache that, you need to compare two different results of the task without redoing the whole work. In general, this could not be solved. So you can check the result without doing the whole. And the closest thing people come is to compare textual comparison of two scripts, which is not reliable at all, and glitchy. But in this case, in case of data forge, it is possible because, as I remind you, that there are no scripts on the metadata, and metadata is basically the value tree. So you can compare two value trees and see if something is changed between those things. And even up to now, there are no such system, even in build system to build tooling, because make files or Gradle, they recompute, they check only the last modified date. They do not check the arguments uh, which were passed to run some task. And you can't, in general, you can't store results, different results for the same task with the different parameters. And that fortunately is possible because you exactly know how your parameters could be compared and how do they affect the task. Of course, you need some, it's called pure functions here. Those tasks must be pure. They should not take any additional external information which could be changed. Let's show you an example. For example, we're in simulation. Well, yeah. The idea is that here we have a push model. So you push data here and it creates. Here we have a pull model. So I do not know about those tasks. I have not said it. I do not know about those tasks when I start the process. I say, please run a task with a given name, with a given metadata, with a given configuration. And it decides which other task it needs to run. Again, it works the same way it works for GNU Make. When you say build or something like that, it initializes a lot of other tasks it depends on. And the tasks and the data processing which is not used in the final analysis won't be invoked. Of course, as I said, it requires some additional machinery and requires, if you start manually changing the parameters of the task from user, it won't work because at least caching won't work. And all this automatic resolution of tasks and caching, and it won't work. Okay, let's see the typical pipeline for simulation. It's particle generation, particle tracing, fraction detector, and then compute, for example, electronics response. And what happens? And the detector geometry changed. It's a typical thing again. And we want to recompute the result. Typically, this particle tracing is more time consuming thing. And in general, we need to rerun it. So, and if we see, for example, that the medium, the particles, the particle generator, the particle tracing of the medium is not changed. The same metadata, the same geometry description, we can restore it from cache. Of course, implementing this thing in practice requires a lot of engineering work to make sure the cache is available. Okay. Mhm, mhm, mhm. It's more or less the same. The problem is, and the difference is again, is how can it's a always the same problem with the caching. How can you understand that your caches needs to be invalidated? In general, as I said, there is no general way to say In this case, the problem could be solved because, as I said, you know exactly all the inputs to this task, and you know it not as some kind of script, as some kind of program, but as exactly as a value tree. So you can compare two different trees of values, and not only you can, and even it is possible that the value tree is changed, but the parameters required by this task are not changed. In this case, you also do not need to reset the cache. I've implemented it in the old version of DataForge. I have not moved it into the new version of DataForge, but it is possible to do. Again, the idea of caching is not new, but the idea how to understand if you need to invalidate cache in this case is very important. As you see, there like it's started like in 2012, and right now the first part of you can find the project on the GitHub. I posted the link, and right now I decided to start using it from scratch. The old version was using multiple languages. It uses Java. It was initially written in Java, and then I used Groovy for scripting, and then I started using Kotlin, and there were some not good decisions. For example, I used Groovy scripts to generate this metadata, and all projects become very tight coupled. And like 3 years ago, I've started a completely new implementation. It's now called DataForge Core, and it's multi-platform. And of course, right now we are mostly using those metadata processing. I mean metadata manipulation and context parts, but the task processing is also there. I just don't have time to work on it right now. A lot of things there, a lot of dreams here. I'm not sure a lot of those things will be implemented. I can say it's an old presentation, but for charts, we are still planning to work with the Kotlin for data science, Kotlin for data team, and implement a common interface for plots in Kotlin. 3D visualization, yeah, we have a perfect 3D visualization. It's a VisionForge project. It's a standalone thing. We do not have root and drop, but maybe we will have it in the future. And most of these things are there. We even have a table API. I'm not sure it will survive because there is now library called Kotlin data frame, and if the inner design will improve, we will deprecate our table API in favor of Kotlin data frame. Okay, it's conclusion. It's some kind of old links, and we are almost out of time, and I wanted to show you some code. Do you have any questions? Sorry. What do you mean by logger? You mean logo? Yeah. Actually, the idea was mine, and I just asked my people from my family who are professional designers to draw it. The idea was mine. Okay, now we will make a quick run of the code itself. You see quite a lot of things here. Oh, sorry. And this this repository is This repository is in my private GitHub account. It's the public repository, but it's not in the laboratory account. It's on my account, and you can see a lot of things here, including, by the way, slow control system. Maybe we will make additional seminar about slow control system and its design. But what's important here is this project, which is called NewMass main. It includes all the analysis logic, and you see different languages mixing here, perfectly fine. And here we have tasks, particularly this one, and we have definition of different tasks which could be combined together. And let's see how it works. For example, there's a select task, which is a task called select, and we have a description for it. It's a nice Kotlin API, and it has a data model. It explains where to take input data for this task, and it says get all the data you can. And it describes a transformation algorithm for the data. The data has a type of data set, which is similar to Spark, how it is called, not data frame, but data set. I think it's called the data set in Spark. So it's something like a directory of data, but the directory which includes possibility to compute. It's a lazy computation that you can compute different elements one by one, and if the one of elements is computed, then it will be remembered. The computation result will be remembered and could be reused. Then you have for example, analyze task, which takes the binary spectra from the detector, and you see that this one takes a new mass set, which is a raw data type for binary data. And this one takes a new mass set and transforms to a table. It's a pipeline task. And here we have a description that it takes on, it depends on the select task. So when you call these tasks, it will call this task automatically. And let's find a more complicated thing. So for example, okay, here it is. More complicated task, more complicated workflow. Here in the model, it checks, it always depends on this one. And if the input configuration in this data field has a specific field, it also loads additional data. So the data actually used in this task will be a result when we start running this task, depending on if we have this configuration parameter. And of course, if there is no data, this task actually what it does, it subtracts the amplitude spectrum for the detector. It subtracts the amplitude spectrum with a neutrino, so it's a so-called dark data. I mean, it's a background. And here we see that if there is no background data, either it is not provided or metadata does not have this flag, this task is skipped completely. So we are not doing anything. And there are other tasks as well. For example, this task, the filter task, depending on this flag merge, it either works with a different data pieces individually, in parallel, of course, or it first merges them together and works with them sequentially, depending on this flag. And you, of course, can create more complicated data flows. There are some design flaws in this idea. Mostly the problem is that how you create this meta configuration, how to avoid errors in this configuration meta, how to make it strongly typed. but the idea is still there. Okay. This is the old code, and you can see that pieces of the old DataForge is still there. You can check them if you want. And the new DataForge project is still, it's not published on the GitHub. It will be in the short time. Right now it's in the space, and we will make it public soon. I mean the new mass. I forgot to open the new version of DataForge. Here it is. As you can see, it has more or less the same structure. For example, it has this DataForge workspace. Probably need to switch to that mode. And we have all those things in Kotlin multi-platform, and we have those tasks, and we have those workspace, which is also a concept of DataForge. You can see, for example, tasks here. It's much cleaner than the old one, but I do not have a lot of time to work on this right now. And the new mass model is there, and we already implemented model things, and even I started to work on the similar thing. I mean the workspace. It's not ready yet though. I'm not sure what is here. Okay, let's see. No, it's not a workspace. It's actually some utility functions. Workspace is not yet implemented here, but there are some scripting mode which allows us to use parts of the system without all this continuous analysis mode. You can see it here. It's a different script. Okay, we're almost out of time, so please questions for the final part. Yes, yes. I think in order to criticize it properly, you need to a little bit more dive into Kotlin. Simple things like you have wrong commas won't work. But yes, please feel free to analyze, and even if you do not criticize it, but just explain some things which I did not explain in the seminar, it will be okay. So yes, feel free. Each you can take each one. You can take old DataForge. You can take a current version of DataForge, and you can take this small project about. Yeah, okay. You just you can just talk with each other and decide. Okay.